Alright, so in one of the last videos you saw how we could convert from a ketone or an aldehyde into an enol. It's actually the intermediate enol that is responsible for the reactivity of, or for this reaction here. And notice what we appear to be doing here. We appear to be taking a hydrogen from the alpha carbon, otherwise known as the alpha hydrogen, and replacing it with a bromine. You can also do chlorine and other halogens, hence the term halogenation, but bromine is very commonly used. All right, and we start off with acetic acid. It doesn't have to be a strong acid. In the process, you generate HBr, so you generate more acid, and that's why this is called an acid catalyzed process. It's kind of auto-catalytic because as soon as it runs once, it regenerates more acid each time, so it just keeps on going. So if we were to remember, well, we know that we can go from here using our acid catalyst, and I'm not going to go through all the steps again, but you can get to here, you can get to your enol. Alright, so if you need a refresher on that, look back at the look at the keto-enol tautomerization video to remember about that. What we're going to focus on here is what happens, alright, when we throw, or when we have the enol, which was generated sort of in situ, how that reacts with the bromine. Alright, so here's our bromine. And this is one thing about enols, and enolates as well. The oxygen could either grab a bromine, giving itself too many bonds. Doesn't really make any sense to do that. What happens here is the oxygen kicks its electrons down onto that carbon, down to that carbon-oxygen bond, giving it too many bonds, but the hydrogen can be removed at some later date, giving it back its two bonds. And if that bond goes down here, you have a Texas carbon here. So what has to happen is that this pi bond has to break. All right, I have to use a different color here. So that goes out to the bromine, breaks that bromine-bromine bond. This step is not reversible. All right, so it's only the formation of the enol that's reversible here. Now, when we draw out this product, let's make sure we can notice exactly what it's going to look like. Most importantly, where is the bromine going to be? Well, in order to answer that, because you can see the double bond here is these two carbons, so potentially I'm not really showing where the bromine's attack, or from where the bromine's being attacked. It's either this carbon or this carbon. So it's got to be bounded in the product to one of these two. It's a common mistake to say, well, it's bound to the middle one. But if we draw out what happens to the carbon-oxygen bond, we can convince ourselves that that can't be the case, because we've reformed that carbonyl group there. Okay, and we've actually given the oxygen a plus charge. So if the bromine that we attacked here can't go on this carbon, it must go on the alpha carbon. Hence, hopefully you can understand the term alpha halogenation, because you've halogenated at the alpha carbon. But not only that, you have also generated some Br minus. It's happy by itself. However, if it sees a hydrogen that's particularly acidic, as it does right here, it's going to go ahead and grab it. So it goes along there, grabs that hydrogen, kicks those electrons onto the oxygen, and ends up giving you this product. Or in fact, it gives you the product that we show up here. Alright. So what we get is it essentially looks like the ketone again, but you could call it the alpha bromo ketone. In fact, that's what some people call these things. The book shows, and I should really specify this, the book shows this molecule as two different resonance structures. So I just want to go into a little bit about that. Two resonance structures here are where the plus charge is on the oxygen or where the plus charge is on the carbon. So I could equally well show this. Alright. The reason I didn't show this one was simply because I didn't want to confuse things any more than necessary. Alright. In this case, the bromine would come attack the hydrogen, break that bond and stick it down onto this carbon-oxygen bond, forming the product. But if you can understand this arrow or these arrows to get to here, then that's what you need to be able to understand. Okay, so that's the final product. That's your alpha bromo ketone. In this case, 1-bromo propanone, I suppose. And that will be a product. This can also be done in base, but the book mainly focuses on this done in acid, and that is an alpha bromination. Bromination at the alpha carbon. Doesn't happen at any other carbon, only ever happens at the alpha carbon. Okay? Oh, and one more thing I should specify as well. In going from here to here, we said in a previous video that you need an acid catalyst, H3O+. The book, I think, makes things confusing by saying in the first step, this is shown in the mechanism on page 687, it shows that the acid is HBr, but you don't see HBr here. That's because HBr is not there. The acid that actually reacts with water to make this is the acetic acid. That's where the H plus comes from. It comes from H3O+. So don't worry about HBr being there because it's not. Alright? Okay, there we go. That's alpha halogenation, a way to add a bromine alpha to a carbonyl group. It's actually a very useful synthetic step. It enables you to add carbons alpha to a carbonyl. You can convert this into, add a magnesium here, make this into a Grignard reagent and add other things alpha to here. And that's not something that we've seen before. We haven't seen Grignard reaction that allows us to be very specific about exactly where we add things. But we'll talk more about that later on in the semester. Anyway, that's a little bit about alpha halogenations. Okay. Bye. It's 1:33. I really ought to get to bloody bed.